There's a contradiction parked on Russian tarmacs that defies all logic of modern warfare. It's a 46-ton giant of welded steel and titanium that first flew when disco was king, a relic that should be gathering dust in museums. Yet this Cold War artifact isn't just activates the fastest combat aircraft anywhere on Earth, and it's become the launch platform for weapons that are reshaping 21st century battlefields. How can a 50-year-old interceptor, designed to hunt bombers that never existed, remain one of the most strategically vital assets in any nation's arsenal? The answer reveals a fascinating tale of emergency design, revolutionary technology crammed into an ancient airframe, and accidental future-proofing its creators never imagined. This aircraft's incredible longevity isn't about simple upgrades. It's about complete mission transformation. A jet born for desperate homeland defense has evolved into one of today's most formidable offensive weapons systems. To comprehend the Foxhound, you must first grasp the spectacular shortcomings of its predecessor. That aircraft was a product of pure fear, constructed mostly from arc-welded steel because Soviet intelligence mistakenly believed America was fielding Mach 3 strategic bombers. Western analysts initially trembled at its published specifications, until a defector revealed the truth. It was essentially a single-mission machine. Its enormous power plants were technological dead ends, so fuel-thirsty they gave the aircraft the endurance of a fireworks display, and a combat radius that was practically useless. But its fatal flaw wasn't propulsion. It was its primitive sensor system. By the 1970s, the real threat had shifted to low-flying penetration aircraft and cruise missiles skimming the terrain. The older interceptor's radar couldn't see downwards effectively, rendering it completely blind to threats flying beneath it. This created a massive hole in Soviet air defenses. They had invested heavily in the world's fastest interceptor only to discover it was strategically obsolete against the actual danger. The MiG-31 therefore was NTA planned evolution. It was an emergency solution born from panic to seal this critical vulnerability. The challenge the new aircraft needed to solve was fundamentally geographical. How do you protect millions of square kilometers of mostly empty territory, particularly the vast radar-free zones of the Arctic and Siberia? The solution wasn't a traditional fighter, it was a flying radar fence. The MiG-31 was conceived as a mobile extension of ground-based air defense networks. The operational concept was revolutionary. A formation of 4 aircraft would link together to create a coordinated patrol line nearly 900 kilometers wide. The key enabling technology was a secure digital data link system. This system allowed the 4 jets to share targeting information automatically without radio transmissions, merging their sensor coverage into one unified picture. This was network-centric warfare decades before the term became fashionable in Western military circles. The data link enabled a form of distributed lethality far ahead of its time. One aircraft could act as a miniature AWACS, illuminating targets with its powerful radar, while other fighters launched missiles in electronic silence. This built-in networking capability, this systems of systems approach from the very beginning, is a fundamental reason why this 1970s design could accept 21st century enhancements. It was a 5th-generation concept trapped inside a 3rd-generation body. To perform this mission, the designers had to create an absolute beast. The aircraft is a colossus whose immense size and weight were direct consequences of the equipment it needed to carry. The airframe itself represents a unique metallurgical mix, nearly half arc-welded steel, a third lightweight alloys, 16% titanium, and a mere 2% composites. The heavy steel construction, so different from the Ltidium American reconnaissance plane it was meant to intercept, was a practical Soviet choice, cheaper, easier to work with, and perfectly capable of handling the intense heat generated at near hypersonic velocities. This massive structure demanded equally massive power, and here the new interceptor made its crucial advance over its predecessor. Out went the inefficient old engines, and came 2 monstrous afterburning turbofans. This was the aircraft's second revolution. These new power plants, derived from commercial airliner engines, gave the interceptor something its predecessor desperately lacked: real range. Suddenly, it could actually patrol the endless Arctic wastes it was designed to protect. But it remained fundamentally a MiG. These engines are absolute powerhouses, each generating over 34,000 pounds of thrust, with afterburners blazing. They're what propelled this 46-ton machine to its maximum speed of Mach 2.83. It's worth noting, this velocity isn't limited by available thrust heats, restricted by temperature concerns. The engines could probably push the airframe past Mach 3, but doing so would risk catastrophic damage to the structure and power of plants. This incredible performance naturally comes at a cost. The fuel consumption is, to be charitable, astronomical. The engines consume kerosene so rapidly that the weapons officer's secondary duty might well be calculating the nearest emergency airfield before they exhaust an entire region's fuel supply. That massive metal airframe, those continent-draining engines, they all exist for one primary purpose. They serve as a high-altitude, high-speed truck designed to carry a single crucial system, the Zaslon radar. This radar is the very soul of the aircraft. It was quite simply the world's first operational passive electronically scanned array radar fitted to a fighter. Its development was exceptionally challenging. The Air Defense Force's requirement to detect and destroy cruise missiles flying at 25 meters altitude against ground clutter was so demanding that the original design bureau failed completely. In 1971, Soviet leadership forcibly transferred the project to another institute who somehow made it work. The electronically scanned array technology proved decisive. Unlike conventional radars that mechanically scan a Daisha process requiring 12 to 14 seconds for a full sweep, the Zaslon could redirect its beam almost instantly. But this 1970s solution was again a brute force approach. The entire radar system weighed a full metric ton. The fixed antenna alone weighed 300 kilograms, double the weight of the American F-14's already substantial radar. To process data from this behemoth, the interceptor received the Soviet Union's first airborne digital computer. This processor, likely possessing the computing power of a modern digital wristwatch, was revolutionary for its era. This entire one-ton assembly of high-voltage electronics and primitive digital computing achieved its objective. It could detect bomber-sized targets at 200 kilometers and, crucially, could track 10 targets simultaneously while engaging 4, even if they were flying at treetop level. The decision to field the Zaslon was a huge gamble that accepted enormous weight and cost penalties because it was the only way to solve the low-altitude detection gap. This choice cemented the aircraft's destiny. It would never be a dogfighter. It was a flying sensor platform, and every other design decision served this master. The interceptor didn't exist in isolation. Its only true counterpart was the American F-14 Tomcat. On paper, they appear similar large twin-engine two-seat interceptors built for long-range combat. But their differing design philosophies reveal everything about the nations that created them. The F-14 was a fleet defender, a guardian for aircraft carriers. The MiG was a homeland protector, a sentry for the entire Siberian landmass. The F-14's radar was a mechanically scanned pulse Doppler system, but it was incredibly sophisticated, able to track 24 targets and engage 6. The Zaslon was electronically scanned, faster to redirect but tracking 10 and engaging 4. The critical difference, however, was in their weapons. The F-14 carried the Phoenix missile with a range over 185 kilometers, an active radar homing. This meant the Tomcat could launch its weapons and immediately maneuver away while the missile guided itself to the target. The MiG, by contrast, initially used weapons with semi-active radar homing. This was a seemingly inferior choice. It required the launching aircraft to maintain radar lock on the target all the way to impact, making itself a vulnerable non-maneuvering beacon. Why this apparent weakness? Because the F-14 was designed as an independent hunter. The MiG was designed as a network component. The simpler guidance was cheaper and perfectly adequate for its intended targets: bombers and cruise missiles that would outperform violent evasive maneuvers. Furthermore, the F-14 with its variable sweep wings was also a capable air combat fighter. The MiG, with its 5G structural limit, was not. As one foreign pilot who flew it described, the aircraft was simply too large and clumsy for close-quarters fighting. The F-14 was a precision dueling sword. The MiG was a two-tone flying sledgehammer. This brings us to operational realities. Like many ambitious Soviet projects, the aircraft's theoretical capabilities often required particular procedures to achieve in practice. It is an exceptionally demanding, maintenance-intensive machine. An Indian air marshal, the first foreigner to fly it, described the weapons officer's rear cockpit as resembling a submarine compartment, complete with a large periscope for outside viewing and dated screens that provided poor situational awareness. But the most revealing and frankly alarming glimpse into its character comes from a friendly fire incident in April 2017. During training, a modernized interceptor locked onto and shot down its own wingman. The official investigation, as always, cited pilot error. But leaked documents indicated a serious technical problem. The upgraded radar and new fire control computer weren't functioning correctly. The system misidentified the friendly aircraft as a hostile target. Ground crews were allegedly aware of this abnormal behavior. The suspected cause serves as the perfect metaphor for Soviet-style modernization. The new processor could unhandle the immense data flow from the enhanced radar. Essentially, the upgraded brain was overwhelmed by the upgraded eyes. In response, pilots reportedly developed their own improvised solution, manually cycling the radar power during flight to reduce the computational load. This is the definition of engineering desperation. To operate the world's most powerful fighter radar, crews had to treat it like a flickering light bulb to prevent it from killing their comrades. This perfectly captures the machine's essence, a titan of raw power, held together by human ingenuity and constant risk. The 2017 incident, while serious, represented a flaw in the modernization process. And that modernization is the primary reason the aircraft remains in service today. It wasn't merely life extended, it was fundamentally reborn. Approved in 2008, this comprehensive upgrade transformed the platform. The original Zaslon was replaced by the Zaslon M. This represented a quantum leap forward. The antenna diameter increased significantly. Detection range expanded dramatically, with some sources claiming it can identify targets at 320 to 400 kilometers. Tracking capacity jumped to 24 targets with the ability to engage 6 or even 8 simultaneously. The vintage computer was swapped for a modern digital processor. In the cockpit, the 1970s analog gauges and the weapons officer's submarine-like periscope were finally replaced with modern multifunction displays, creating a true glass cockpit. This new sniper required a new bullet. The modernized variant carries a hypersonic missile capable of reaching Mach 6. Its engagement envelope stretches from 150 to 400 kilometers depending on the attack profile. Crucially, it solves the original guidance limitation. It features an active radar seeker, allowing it to guide itself during the terminal phase. This combination, the 400-kilometer radar and the 400-kilometer missile, justifies the aircraft's continued existence. It creates a sensor-shooter pairing at extreme ranges that remains unmatched. The upgraded interceptor is the only air combat system worldwide that can detect what it can shoot and shoot what it can detect at this extraordinary beyond visual range distance. This has transformed its mission into that of a dedicated AWACS hunter. It's designed to eliminate high-value, low maneuverability assets like airborne early warning planes, tankers, and command aircraft from distances well beyond their protective fighter screens. This isn't theoretical. This specific system has reportedly been a primary threat in recent conflicts, achieving multiple long-range kills and forcing opposing pilots to fly dangerously low to avoid detection. As if this rebirth as the ultimate long-range sniper wasn't remarkable enough, the aircraft's brute force 1970s design granted it a second, even more strategically significant new life. This variant isn't an interceptor at all, it's a strategic strike platform. The specialized version serves as a carrier aircraft modified to launch one specific weapon, the Kinzhal or dagger. This is an air-launched ballistic missile, a modified version of a ground-based system. It's nuclear-capable, travels at hypersonic speeds approaching Mach 10, and has a staggering range of 2,000 kilometers when combined with the aircraft's own performance. To carry this monster, the interceptor is radically altered. It's stripped of its core identity. The massive Zaslon radar is removed. The internal cannon is deleted. All air-to-air missile pylons are eliminated. In their place, it receives additional fuel capacity and superior communications gear to accept targeting information from external sources. This variant's sole purpose is to function as a reusable first stage. It performs the one trick it has always mastered: flying extremely fast and extremely high, giving the missile the initial velocity and altitude needed to achieve its advertised performance. This capability fundamentally alters strategic calculations. Launching a ballistic missile from an unpredictable, high-speed aerial platform makes interception infinitely more difficult than targeting a fixed ground launcher. Thus, the aircraft's original limitation being a clumsy, non-maneuvering titanium dragster built purely for speed and altitude became its single greatest 21st-century asset. The 1970s solution for countering high-altitude reconnaissance planes, accidentally, became the modern solution for deploying strategic hypersonic weapons. So why does this aircraft remain operational? The answer is that the original 1970s interceptor no longer exists. The vintage airframe has proven an incredibly durable and adaptable foundation. This has allowed it to evolve into 3 distinct, highly specialized, and lethally effective versions, sharing a common structure. First is the original interceptor, the Cold War Sentry, now largely upgraded or retired. Second is the Sniper, the modernized variant. This is the 21st century AWACS Killer, a networked platform creating a 400-kilometer no-fly zone for critical Western support aircraft. Third is the Striker, the ballistic missile carrier. This is the radarless strategic weapon, a reusable booster whose only mission is to hurl its hypersonic missile toward distant targets. The Russian military plans to maintain these airframes in service until at least 2030, having already extended their operational lifespan. While a modern stealth fighter like the F-22 Raptor would be virtually invisible to the MiG in direct combat, the American aircraft cannot perform the MiG's unique missions. It cannot patrol the vast Russian Arctic without an enormous tanker fleet Russia doesn't possess. It cannot carry 400-kilometer range, active homing missiles, and it certainly cannot launch a 2,000-kilometer range ballistic weapon. The aircraft endures because it represents the ultimate expression of a specific brutalist design philosophy. It was engineered for a niche role: high-speed, high-altitude, heavy payload that the world assumed was obsolete. But by being absolutely superior at that one seemingly outdated specialty, its fundamental performance characteristics became the perfect accidental solution for 2 new 21st-century missions. It remains in service because for the very specific, very demanding tasks it's assigned, no other platform globally can compete. Yet behind this narrative of accidental genius and adaptive rebirth lies a more sobering truth. The fleet is not immortal, and its future is far from guaranteed. Russia inherited roughly 370 airframes from the dissolved Soviet Union in 1991. Today, fewer than 130 are believed operational, with perhaps 150 total remaining in inventory, including those in storage or undergoing upgrades. The attrition has been severe not from combat, but from relentless aging, maintenance challenges, and the chronic underfunding that crippled Russian military aviation through the 1990s and early 2000s. Every remaining aircraft is now a precious, irreplaceable asset. There is no active production line to build new ones. The factories that manufactured these machines fell silent decades ago. The specialized tooling is gone. The expertise has dispersed or retired. The supply chains have dissolved. Every airframe lost to accident, every jet that reaches the end of its structural life, represents a permanent capability reduction that cannot be recovered. This creates a strategic countdown that grows louder each year. The modernization program, while impressive, also demonstrates the limits of what's achievable. You can upgrade the radar, replace the computers, and install new weapons, but you cannot alter the fundamental metallurgical reality of a structure stressed by decades of high-speed flight. Steel members fatigue, welds develop cracks, titanium components corrode in ways difficult to detect and impossible to fully repair. The Russian Air Force has reportedly extended the operational life of the fleet to 40,000 flight hours per airframe, a figure that sounds impressive until you realize it's being extracted from machines originally certified for significantly less. This isn't engineering confidence, it's necessity disguised as capability. The maintenance burden increases exponentially as the fleet ages. The 2017 friendly fire incident wasn't an isolated anomaly, was a symptom. It revealed that even the most critical upgrades, the new radars and computers intended to keep these machines relevant, are being integrated into airframes and systems fundamentally strained by the demands placed upon them. The fact that pilots reportedly developed unofficial workarounds manually toggling radar power to prevent fratricides isn't a testament to Russian resourcefulness. It's evidence of systemic strain, a fleet operating at the very edge of reliability, sustained by institutional knowledge and improvisation rather than sound engineering practice. And yet, the harsh reality of geopolitics ensures these machines will keep flying. Russia has no viable alternative. The program intended to replace them remains a paper concept. It has been in development for over a decade and has produced nothing but digital renderings and optimistic announcements. The program is reportedly stalled, underfunded, and lacking critical technologies, particularly in advanced electronics and propulsion. Even if it eventually succeeds, serial production wouldn't begin until the late 2020s at the absolute earliest, with initial operational capability following years later. By the time a replacement arrives, if it ever does, the existing fleet will be so depleted and aged that a massive gap will emerge in Russian air, defense, and strike capabilities that cannot be filled. This is the true paradox. The aircraft is simultaneously indispensable and unsustainable, a machine that must continue flying precisely because nothing can replace it, even as every flight hour brings it closer to physical failure. Russian military leadership understands this, which is why they're ruthlessly prioritizing the most capable airframes. The missile carriers receive the best maintenance, the newest components, the most careful handling. They are the strategic crown jewels. Similarly, the modernized interceptors are being preserved and enhanced in preference to older models. The original baseline aircraft are being quietly retired or cannibalized for parts to keep their more valuable siblings airborne. This is triage, not transformation. The fleet is shrinking, and within that diminishing pool, resources are concentrated on platforms delivering the highest strategic return. It's a rational response to an impossible situation, but it's also a visible countdown. In perhaps a decade, maybe less, the number of operational aircraft will decline to the point where they can no longer effectively perform their missions. Arctic patrol lines will develop gaps. A WACS hunting will become impractical due to insufficient numbers. The hypersonic strike capability will diminish to a symbolic force. When that day arrives, the 50-year saga of this Cold War giant will finally conclude, not with a dramatic finale, but with the quiet grounding of the last flyable jets due to metal fatigue, parts shortages, or the simple reality that too few remain to matter. And when that happens, the world will witness something significant. It will mark the end of the final operational aircraft from the golden age of Soviet interceptor design. The retirement of a warfare philosophy that prioritized raw speed and massive payload over stealth and agility. The aircraft will take into history a unique combination of capabilities that may never be replicated. No future platform will likely match its specific blend of sustained high-speed performance, extreme altitude capability, enormous radar power, and the ability to network multiple aircraft into a cohesive 1,000-kilometer patrol line. These were solutions to Cold War problems that no longer exist in their original form. Yet, paradoxically, they became solutions to 21st-century challenges that didn't exist when the aircraft was designed. That accidental relevance, that bizarre second life as both an AWACS assassin and a hypersonic missile truck, was a gift of physics and engineering that cannot be deliberately recreated. It emerged from a specific convergence of Cold War paranoia, Soviet industrial capacity, and doctrinal needs that will never align again in quite the same way. The lesson here isn't that old aircraft can always be upgraded into relevance. Most cannot. The lesson is that sometimes, if you create something utterly uncompromising in its pursuit of specific performance goals, even if those goals seem obsolete, to create a tool that can become unexpectedly vital when the world changes in unanticipated ways. This aircraft was never intended to be a strategic strike platform, but its ability to fly at Mach 2.3 at high altitude made it perfect for that role. It was never designed to hunt command aircraft 400 kilometers away, but its combination of powerful radar and long-range missiles made it uniquely suited for precisely that mission. It survived because it was so exceptionally capable at its original purpose that when new missions emerged requiring those same extreme performance parameters, no other system could fulfill the requirement. That is the final contradiction. It's a machine that should be obsolete, that by every reasonable measure is obsolete, but remains critically necessary because the particular type of obsolescence it represents happens to be exactly what S needed today, and that is why, for a few more years at least, these 50-year-old titanium giants will continue to thunder down runways across Russia, carrying either hypersonic weapons skyward or hunting high-value targets at distances modern fighters can scarcely comprehend until the final day arrives when the last one inevitably falls silent. If you found this deep dive into one of aviation's most fascinating paradoxes compelling, please support our channel. Hit the like button and subscribe to Winds of Thought for more content that explores the hidden stories behind military technology.